Hi. This is the basic outline of our class. I'll discuss some of the basic science concepts. Then we'll move on to diagnostic technologies, which has revolutionized diagnosis. And then we'll talk briefly about treatment options and then devices and some of the future trends. So let's jump right in. Okay, my name is Dr. Bharat Pathiji. I came to the United States in 1973 at a mature age of 23 and trained in cardiology and practiced in a place which has been in the news. I'm sure some of you have heard about the Alex Pretty, and he was from Preble High School, Green Bay, where I practiced. And in fact, he went to school with my son. They were both on the track team and graduated in 2006. And this tragedy reminded me of what I saw when I was about your age and was migrating. These were the scenes from a place that even your parents may have been too young to remember, at a place called Kent State. But again, it just jogs memories and some of a personal story. But one thing, and that was protest to war in a place called Vietnam. But one thing you have to say about wars is that they're great for medical advances, starting from the Florence Nightingale, who improved nursing in the Crimean War, to the shell shock and plastic surgery, in First and Second World War, along with advances in antibiotics such as penicillin and blood transfusion technology in Second World War, mobile surgical units that took place in the Korean and Vietnam War, and obviously the advances in learning about post-traumatic stress disorders. And so, except for a direct shot to the brain, just about all of the technology, so saving lives, has been a dramatic change. And this gives you an example of advances in cardiac surgery during the Second World War. Dr. Dwight Harkin was drafted, and he was distraught with the amount of shrapnel injuries to the heart. Now, at that time, there was the old axiom that one cannot operate on a beating heart that would stop even if you touch it. It was the seat of soul. And he decided to do something about it and started operating on a beating heart with trying to beat the clock, so to speak. And by trying to uh, operate within a span of 4 minutes about removing. Okay, and he's didn't have much success. His first 14 patients died, but luckily for humanity, those were dogs. But later on, he saved a countless number of lives. And later on, after returning to the United States, advanced a valvular heart surgery. And as we'll talk about later, heart valve disease can be related to infections from strep infection, which has now actually disappeared with widespread antibiotic usage. Okay, so now basically, heart is the center of life. Now, we, as you know, general belief is that life begins with fertilization and conception. Okay, now, and the unit of life can, in what the discovery of microscopy was thought to be a cell. Okay, and this was the axiom in the 19th century. All life begins with cell, and in fact, the beginning of ovum is also primarily cellular. We all started as a unicellular organism and gradually morphed into multicellularity. And so now, then, when I went to school, there was just a little mention at the end. By the way, there is something called DNA inside the nucleus, and that has a lot to do with the information. Now, this information was not only just Watson and Crick, who were inspired by this book by a physicist named Schrodinger. I'm sure if you took physics in high school, you may remember the Schrodinger's cat, the thought experiment as to whether uh, the cat is alive or dead. And this was also addressed by Alan Turing, the founder of uh, computer science. Okay. Now, how does the body get information from outside to inside? Primarily due to senses and with nervous system, and the nervous system reacts in two ways: sympathetic, fight and flight, or rest and digest, parasympathetic. Okay. Now, what about energy? When I went to school, the thing was metabolized was, well, you generate ATP molecule, and it is broken down. The food is broken down by complex chemical uh, cycle called Krebs cycle. And that was the horror of medical school students. You memorize it one day and forget it next day of various amino acids, that are synthesized in multiple steps to generating ATP molecules. That's where it was at. We had no idea as to how ATP actually functioned. And this was, the neurologist did something about it as to how the signal was transmitted by electricity. In 1940s, two guys named Hodgkin and Huxley worked out the electrical properties of uh, current inside a nerve fiber. And this goes back to the early days of electricity, which was done on frog leg experiments back in Renaissance and Enlightenment, Italy, by guys that names you very well recognize, such as Galvini and Volta. Okay, and but cardiologists were lagging behind because we did not have correct instruments in recording the signal electrical properties of the heart. And back in the 70s, 80s, knowledge about ion channels became available. And some of the new terminologies that now we are encountering, those were foreign when I went to school, such as bioinformatics and bioenergetics. And now again, one can just say basically define the mode system. The cardiovascular system is the pump of the heart, the left and the right heart that you studied in school. Okay, and moving on to a liver, which digests all the food that you take in all the three basic food groups. And the liver also works as a detox center. If you eat something that is disagreeable, liver is forgiving. And nature has evolved, given capacity to the liver to metabolize all the toxins that we may knowingly or unknowingly consume. And also now to eliminate all the waste products, you need the kidneys, and which are connected. Now, when we were in school, everything was compartmentalized, like the Hatfields and McCoys. We know people didn't talk to each other too much. There was, but now we are learning that kidney disease is intricately related to heart disease, and metabolism is integral part of, in fact, so much so that official terminology is CKM disease has been coined, such as cardiac, kidney, and metabolic syndrome. And all of this is obviously controlled by brain, which has a huge effect on all the organs, sort of master orchestra player. So that just gives you an idea about the border between, this is all you've got to do with the energy utilization as the body tries to maintain energy balance, homeostasis. So while doing work, the energy is not lost and it's conserved and tries to maintain the balance. Now, this is just an outline of cardiology for engineers. Heart, one can imagine the heart has two pumps working in sequence, right and left, the impure versus pure, oxygenated versus deoxygenated blood. And that goes down from the pumping chamber to varieties of tubes that are laid down. The aorta is about as big as 3 finger breadth, going down to narrower and narrower size. When we get down to the capillaries, we are talking at levels of few microns, as you can see. So those are hard to visualize, but that's where the oxygenation and nutrition exchange take place. So now, how can heart get diseased? Two ways. Either it is working too hard or not hard enough. And there are various valves inside the heart, primarily four valves, and they can be either narrow or leaky. Okay. And the same way in blood vessels, at points where the blood vessels curve, there can be blockage that can develop due to scar tissue or cholesterol plaque. And so that's basically the disease process, which you can synthesize in terms of engineering. And engineers have played a role in creating various fluid dynamics models. There is a freestanding institute called Santa Fe, which takes a multidisciplinary approach and based on various models about in a complex three-chamber heart or four-chamber heart rather. They have created three-dimensional models of the fluid flow, and this is difficult to create and visualize because it is affected by the various factors, not just Newtonian flows, but diffusion capacity and this vessel wall, as well as the viscosity of the liquid, that is blood in this case. And so the pressure volume relationship has to be optimized and modeled. And this is done based on complex Navier-Stokes equations that I'm sure you guys know more about it than I do. Now, interestingly, the shape of the heart has a big role to play as well. And then the heart, if you look at the bottom, it looks like a various loops that are around, and it looks like a shell formation. Basically, it's a spiral inside and outside. Now, nature has a love for spirals. You can see that in a shell on an oyster or snail. At the same time, you can see it in sunflower. So this is the capacity where actually the heart gets smaller in size and squeezes out blood. Okay, so it's almost, and this is an interesting property, that improves the functionality of the heart. And this breaks down to the mathematics that goes back to Fibonacci sequence and the standard row. And this dates back to the evolutionary root of cardiac muscle. Now let's just briefly talk about the evolution of the heart. Now we all started out as the small worm, basically, or earliest multicellular organisms, and in that the heart was basically like a tube that pumped blood, from up top, from front to the bottom, as you can see in the middle. A fossil that was discovered in China, Fuxinhua protensa, it shows a complex organ system, a tube that runs from front to the back. Then later on, when evolution of fishes came, the heart started becoming segmented and pumped about, took in oxygen from gills, and later on pumped to the body, so improving the efficiency. Similarly, when getting down to the amphibians, a three-chamber heart developed, and again, you can just see that the muscle fiber or like a various tubes that folded on itself, so that you can see how the snake type shape that takes place on a so-called knot that occurs. Now, this is the macroscopic appearance, where at the microscopic level, that this is related to varieties of cells, something called the pacemaker cells and the muscle cells, which are all interconnected, and along with other scaffolding that is devoted by fibroblasts. So the evolution goes back to about 500 million years. And so all the disciplines of not just DNA, muscles, cells, and the shape of the heart, they all come into the ring. And people who are more physics and mathematics oriented have taken advantage of this by trying to improve the shape of the heart. The shape of the heart can be, one can say that the normal heart looks like a football, okay, and that squeezes from the bottom up and to increase the flow forward and in upward direction. On the other hand, the diseased heart almost looks like a basketball around, so it loses its efficiency. Okay, so moving right along, and these principles were worked out long ago by British physiologists to the optimal relationship between pressure and volume, and varieties of curves were done based on frog heart experiments as to what is the ideal pressure, where as the pressure increases, the volume increases, but at a certain point there is a tipping point, and beyond that, if the pressure volume relationship falls apart and the volume reduces, so you fall off the curve, so to speak. Okay, so this is the physiology of it has been worked out by measuring the tension in the muscle fibers and the optimal length of the individual sarcomeres where the tension develops, and this was okay. And now similarly, the tuberculations, it says again evolutionary roots that were related to chimps, but the chimp's heart has a lot more tuberculations. Okay. On the other hand, the human heart is more elliptical and has a smooth wall, and so in that way we have a better efficiency of the heart, so we can generate more force and a faster rate at the same time. So we can see how on the curve the tuberculations ratio, okay, the apex is different between a chimp and humans. So that gives us the evolutionary advantage that we can outrun a chimp very easily. Okay, so one can say that nature has solved the flow equations by trial and error of evolutions over millions of years. Okay, now we talked about the force and volume relationship, but at the same time, the rate is equally important. And you can see that there is a mathematical relationship between the shape and and the heart rate as well. Okay, and as the smaller the animals need faster capacity to for the so-called fight and flight response. And this was worked out again in the 30s by something called the Kleiber's law. The metabolic rate is the 3/4 of the power of the mass. And so there is something called the finite heartbeat relationship. Like the heart, humans and chickens have around like 2 billion heart rates. And as the animal becomes larger, the heart rate drops. Okay, and in other words, you're uh, pretty big. Okay, then you are not much threatened much, so you can afford to take things easy and slow and steady wins the race, so to speak, as opposed to the life in the fast lane for hummingbird, which has a heart rate as high as at 1,200 beats per minute. Okay, now again, you can see on this curve that the humans are outliers simply because due to technology, we have changed made in the paradigm shift. Okay, and again, just for demonstration, you can see the whale's heart, which is huge by all standards, 5 feet by 4 feet by 4 feet and weighing 400 pounds, beating at a leisurely pace of about 8 to 10 beats and pumping 58 gallons of blood per minute, and compared to the poor hummingbird, which weighs 4 grams and the heart beats at 80 beats per second. So now this is a show and tell of virtual reality. You can see the heart in various views, rotating the two atria at the top and the various valves, the so-called right-sided valves and the two valves on the left side, and the big aorta, the top chamber on the right side called atrium. Okay, all these terminologies are Latin related. Okay, and the various blood vessels that are connected to the lungs, and the light that you see is the spark that starts. Okay, and the impulse transmission. Okay, now this is not just for show and tell, but it's useful for a diseased heart, especially in a child with deformity, that gives the surgeon a clear-cut idea as to how to operate, and he can visualize the individual anatomy and so-called personalized medicine, and can operate with the VR glasses. Now, again, not to belabor the point, but to emphasize the need for energy. The heart is an energy hog, similar to brain, and those are the organs that can develop disease very quickly. Heart use up to 20 kilograms of ATP per day. That's a quick turnover, and all this energy is, comes from food and nourishment, primarily glucose, and this is metabolized in the mitochondria, the so-called oxidative and phosphate reaction. Now, the mitochondria are the workhorse for energy of all over the body, and much more important, and the heart muscles are densely packed. And the mitochondria is a genome which you inherit from your mother, is quite small, but is extremely important. It's only about 37 genes, and it has a huge role to play in calcium metabolism. And if there is any abnormalities, that can cause life-threatening arrhythmias, abnormal enlargement of the muscle, and so much so that in vitro fertilization, there is now a technological advance of something called the three-parent baby, so that the diseased mitochondrial genes can be eliminated, and the abnormalities that can be involved in free fatty acid and carbohydrate metabolism can be removed. Okay, and again, if the mitochondria, can react to reactive oxygen species, and if the metabolism is abnormal, okay, and this is how the inflammation plays a huge role in causing heart disease as well. Okay, and this is a little electron micrograph of mitochondria. You can see the top one. This is the cardiac muscle, which is densely packed with muscles, and then the axon of a nerve fiber, and again the adrenal gland, which helps you respond to stress and strain, again has a moderately high number of mitochondria. Okay, now this is the biochemical way of metabolism as to from aerobic and anaerobic. The aerobic metabolism is much more energy efficient. You can generate for one molecule as many as 36 ATP, while the anaerobic is far less efficient, generates only 6 ATP molecules. Again, so the mitochondrial dynamics is quite important in the cardiovascular health, and again, this has a big role to play in smooth muscle proliferation, heart development, and differentiation of the heart muscle cells. Okay, and again, this is very temperature sensitive phenomenon because that's one of the reasons, and the classic, that's why during cardiac shock the body is cooled down dramatically to reduce the oxygen demand. Okay, and there was the most dramatic example was of a Swedish skier who had a skiing accident and was dead for almost 80 minutes, and finally was clinically dead for a number of hours, and was revised using heart bypass and revolving technology, and suffered a brain damage. It took us about 8 months, but she did make a final recovery. So the saying in emergency medicine is that you're not dead until your body temperature. So that is very important for drowning victims or hypothermia related death. Okay, and so this is rather busy slide. That if you have, and you can just see as to at various cells, as it develops from oversight to this thing, and the role of energy is mitochondria is dramatically important. You can see these are the granule structures that mature and provide energy through oxygen ox-phos reaction. Okay. So that's so much about the energy. Now, when we talk about the technology, the earliest rise of technology was, a hollow tube, which was used as far back as 1816, when a French physician named René Laennec, he rolled up a tube and made listen to the heart and magnified the sound. Okay, so this was the start. And before that, even a couple of hundred years before that, finally the circulation was defined, and the old concepts of liver being the center of pumping blood was put to rest. That went back to the days of Galen and Aristotle. Okay, and now for the future is for uh, to a heart has very human heart has very limited capacity for regeneration, and due to shortage of organs, the transplant technology is being considered, and the pigs are closest in terms of size to the humans. So, but they harbor varieties of diseases, and the genes are being removed with CRISPR technology, and so that way a made to order pig heart it can be injected with human pluripotent cells. Okay, and that can be used in future, but that's still now the pig kidney has been transplanted, but the heart is still further down the line because it's a lot more complex involvement that takes place. Now, in medicine, we are, but people tend to be conservative, and we tend to make, you know, an educated guess based on the amount of information that is available. And in fact, sometimes, we have a logic which is rather simplistic without paying attention to the metabolism complexity of the evolution. Just to give an example, when the early days of diabetes, people detected sugar in the urine, they thought it would be very important to just let people eat the sugar and replace what is missing. And obviously, that did not work out so well. Similarly, with the discovery of insulin, the pancreatic juice, which was useful for digestion, again, but we did not understand that the insulin is lipogenic and improves the metabolism and contributes to obesity, and again aggravates the inflammatory processes that goes along, and while you may live longer, but again it leads to further atherosclerosis. Okay, varieties of discoveries that have played a role in cardiology, electrocardiogram, ultrasound. So every new technology that came around, cardiologists have borrowed the ideas and have used it to their advantage. As you can see with the Manhattan Project and nuclear medicine, we started using that for diagnosis. And at the same time, CT scanning became available. The latest gadget would be the magnetic resonance imaging. So all of these technologies have been useful. And last but not the least, with the advances in X-ray, we started injecting contrast material to see where exactly the blockage was. And with the discovery of, and later on, we talked about with the artificial uh, oxygenation and the heart lung machines, the advances in open heart surgery took place, and the various devices, including pacemakers and shocking devices and defibrillators. Last but not the least, the new drugs have come into the market, including monoclonal antibody technologies are being used in cardiology. The earliest rise of technology was X-rays that mechanical engineer named William Röntgen was working with cathode ray tubes, which were in the 19th century. And at that time, even though his equipment was covered, he saw a faint glow of while working with cathode ray tubes, on light sensitive material. Well, when he was able to take the image on a barium salt photographic plate, and he just thought this was something unusual. He didn't understand the basic science of it, so he labeled it as X-ray, which was photons. Okay, and he asked his wife to take an image, and you can see the picture of his wife's ringer. And obviously, she was frightened with this thing. And this technology very quickly got caught on, and the orthopedics started using it for bones uh, and diagnosing fractures. And later on, again, is that it happened that there was abuse of technology. The X-ray is very widely used, even for making sure that your shoes would fit properly, without realizing. Now, there's history of Nobel Prizes is worth mentioning that Alfred Nobel was an arms manufacturer all over Europe and was a multimillionaire and had factories on both sides of the Atlantic. Now, when his brother died, a French newspaper published an obituary that the merchant of death uh, is is no more. And Alfred read this and he was shocked that this is how he will be remembered. So that's when he decided to donate his fortune. Okay, and so nitroglycerin was one of the earliest medicine that was used as a vasodilator, but the mechanism became apparent much recently, and I'll mention that later on as we go along. Now, the X-rays can be used to detect not just bones and other structures which are radio opaque, but with something called the dual image X-rayography, we can diagnose the difference between the body fat, and this is used in various gyms to see the body fat composition. And but the electrical properties are different because tissues with more water conduct electricity better that have lower impedance, while fat resists because of and has higher impedance. That has led to the development of smart scales and handheld sensors to estimate the fat-free mass and the body fat percentage. And this gives us an idea that as to different ethnicities have different fat distribution in the body, and that has a direct relationship in the amount of heart disease that is prevalent. Okay, now on the tails of the neurologists and the muscle physiologists, various British physiologists uh, did an experiment of recording impulse from the heart. Okay, and again the signal recording devices were rather crude, but they kept working on it. And this was like you can see, this was some of the earliest experiments that were done by a physiologist named Waller, and he did a demonstration with the Royal Society, one of the oldest scientific society in London. And here is his dog in 1909, standing in the salt water, and they're trying to record with a string galvanometer. Okay, and the people who were against the cruelty of animals did not think highly of it, and even was questioned in the British Parliament. Now, Waller himself, even though this was a show and tell type of thing, he did not think that would have much rule. But other scientists, a Dutch scientist named Eindhoven, uh, decided to take up the mantle and continued to amplify the signal and record it in a much more reliable fashion from a larger uh, animal, i.e., human beings, and was able to work amplify the signal dramatically enough to record it on moving paper that was connected. And this was again a behemoth of a machine weighing about 500 pounds and requiring 5 people to operate with a small beam of light shining on a string galvanometer on a photographic paper. Okay, and but now again, with miniaturization of technology and improving of the signal recording, you know, with this two simple electrodes can be recorded with your Apple Watch and can make precise diagnosis. Now, the pattern recognition that evolved is a dramatic intellectual triumph of humanity. As you can see, that the heart impulse starts with the pacemaker cells, which are at the top of the heart in a place called the sinoatrial node. And these have spontaneous automaticity, and that the impulse gradually travels in a waveform formation to the middle and downstream and through the big muscles on both sides simultaneously. And the signal, with the larger muscle generates a bigger potential. And based on this simple pattern recognition, and for some reason, Einthoven decided to label these waves uh, with the last part of alphabet PQRST. Okay, and that has stuck with time. And and so this is the average cardiac cycle, systole and diastole. Okay, it takes place. Okay, and the first day. Now, there can be varieties of diseases that can be diagnosed based on simple pattern recognition. Okay, and these are the diseases that we'll talk about in the next few minutes. And this is how the heart pacemaker, the sinoatrial node, which has the automaticity. Now this list starts rather backwards. In phase 4, which is this called spontaneous depolarization that takes place due to sodium channel leaking. Okay, and then the action potential reaches the baseline, and when it is the threshold, then the other potassium and calcium channels operate, and in the action potential rises to the peak, as you can see, the phase 0. And when it reaches the top, then the calcium channel close and the potassium channels open. And this is the phase 1 and 2 that takes place inside the cardiac muscles. And so this is, and then when the potential reaches again below the threshold, then the spontaneous depolarization takes place, and the whole cycle starts again. On the other hand, compared to the pacemaker cell, in the muscles, the action potential rises abruptly and reaches higher, okay, and comes down. So this is a more sodium channel. So there is clear-cut differences. And so this is, you can just say that this is the secret of life, so to speak. And this has evolutionary basis due to the fact that the life evolved in sea, and that's where this role of sodium and potassium has plays a dramatic influence on generating impulse. Okay, and now similarly, now this is an important thing that you can just explain in more in detail. At phase 4, sodium and potassium channels are closed, and and the muscle potentially stable are at -90. When the influx of sodium that comes in that you through open fast sodium channels, and the potassium channels are transiently open, and again the transmembrane potential returns to 0, and then the influx of calcium tunnel takes place. Okay, and there's an interplay between the two channels that takes place between calcium and potassium, and then again the potential returns to the base. Now, during certain part, the heart muscle is refractory, means that no matter how big a stimulus that you give, it will not react. And later on, there is a part where the heart muscle is vulnerable, means an impulse that is given during that part is hyperexcitable and will cause rapid firing. Okay, now these properties have a big role to play in causing diseases. Okay, and we'll address that in just a few seconds. Okay, and here's the microscopic view of the cardiac muscle. Okay, you can just see here that the cardiac muscle has striated, means as and organized into sarcomeres, the individual muscle fibers, and has a banding pattern similar to the regular muscle. Now it has also something called the intercalated disc, and that contains gap junctions, and that allows the impulse to jump from one band of muscle fibers, so they can work in synchrony and in harmony, as we talked about the shape of the heart earlier, and that allows the depolarizing current produced by the ion flow to the next, and is in the so-called electrical coupling. It allows the quick transmission of the action potential and coordinates the contraction of the heart. Okay, and so these things are nicely anchored so that the cells don't pull apart due to the stress of muscle fibers contracting. Now, the varieties of abnormalities of this impulse formation has led to a sudden death. Fortunately, it is rare, and varieties of prominent people. One of the rock singers died on the stage, and various hockey players and basketball players have had a bad. And you can just see that based on this pattern recognition, the impulse occurs slightly out of sequence in a few milliseconds apart, and it sets up the short circuit, and the heart goes berserk and beats at a rate almost uh, greater than 200 beats per minute. Just to give an example, the normal range of the beating of the heart is anywhere from low of 40 to a peak of 160. And you can see for exercise stress testing, it is 220 minus H. That's the normal range for human heart. And if the delay in the middle does not take place, then the impulse goes around in circuits and something called a phenomenon called reentry. These are the common arrhythmias that take place, and the heart rate can be as high as 300 and can be very quickly fatal because the heart does not have time to fill up with appropriate amount of blood and you pass out very quickly. Now, fortunately, this conduction is sensitive to stimulation of vagus nerves, and this was rather dramatic when we're in training, this response to the stimulation of vagus nerves, and that is can be done with simple massage on the vagus fibers that are under in a place called carotid sinus in the neck. And if you come in and if you are able to just impart just enough gentle pressure on the carotid sinuses, that you can stop the short circuit and you almost look like a hero. Okay, so this is one way of treating the rapid heartbeat, and there are varieties of drugs work on it. Some actually prolong the cycle length, increasing the reentry, and this can be a side effect of various drugs. An allergy drug called Selden that was marketed in the 90s had the potential that it affected the cycle length of the heart and causing reentry of the impulse, leading to a sudden death. And these are due to ion channel abnormalities. And so now it is mandatory that all the new drugs that are marketed should be tested for it. And this can occur even in simple SSRI, the antidepressant drugs, and some of the antibiotics, which is that we can have a similar effect. Now, another way how mechanical energy can be converted into electrical energy is that, as I mentioned a little while ago, during the vulnerable period, if the impulse comes on the heart, such as injury directly to the chest wall with hockey puck or baseball, usually occurs in teenage boys or girls for that matter, okay, that can set up the short circuit, as we can see from this little cartoon diagram, that the impulse comes in right time and the heart muscle goes berserk and beats out of sequence in a chaotic fashion. Okay, and that really quickly leads to passing out, and unless prompt defibrillation is offered, it can lead to sudden death. Okay, and similar problems occur in various South Asian ethnic community that there are various channel anomalies that occurs in, and that can be again diagnosed by surface EKG. Okay, and so the impulse formation and the timing is extremely important and is exquisitely controlled by evolution. Okay, now let's see. Hope this movie plays. This was a simulation that was generated by the FDA research laboratories of cardiac fibrillation using varieties of pixels and computational mesh to demonstrate rabbit heart geometry. Okay, and this demonstrates cellular processes. Okay, and that shows the fast sodium channel current monitoring and repolarization. Okay, and again towards the end, it shows also the chaos that took place in the ventricular fibrillation. Okay, let's hope that it plays. It's There's no sound, by the way. Right and left heart, as you can see, the wave formation. There is a clear pattern to it, rather fast, but one can see that the impulse starts and goes up. This is the chaos that you can see in the ventricular fibrillation, that the pattern is totally dramatically different, altered. And so the ion channels, there are varieties of ion channels, not just sodium, potassium, and calcium, but there are, hundreds of channels have been discovered. Some are voltage dependent, some are ligand dependent. Ligands are the small protein-based molecules. And there are mechanical channels which are sensitive to temperature, pH. Okay, and so and they play a dramatic role in transmitting information. And varieties of drugs that are used commonly in medicine, are worked through the most common drugs, which are called calcium channel blocking drugs, which are some family members have used for blood pressure monitoring, work through this. And then when you go to the dentist, when you get the lidocaine, that works by blocking the sodium channels, blocking the pain response. And various antiarrhythmic drugs also work. So the same principle that physiology uses and evolution has used, we have used it successfully for therapeutic purposes. Now, sometimes this is an interesting point that you may enjoy. A blood pressure drug which was marketed in the 80s and 90s, called minoxidil, which had side effect of fluid retention and was never caught on properly. But patients who took that experienced hair growth, and that was used as a marketing drug for baldness, and which you may have heard about, called Rogaine. Okay, and then varieties of other methods are used for treating channel-based disorder, including gene replacement and antisense oligonucleotide, allowed. And and varieties of other CRISPR-based technologies are being used, but they have a limited role in treating only a monogenic diseases. Okay, and and there is a future role for bioelectricity in optogenetic approaches also for treatment of some of these disease processes that way just outlined. Moving on to radiology, the earliest, as I mentioned earlier, it was considered a taboo of touching a beating heart. And this was a challenge by a German uh, physician, who introduced a catheter in his own heart, as you can see from this picture. And he obviously lived and was able to get a plain X-ray, and proving that yes, that heart, this can be treated. He introduced a rubber catheter, and the catheter technology has advanced dramatically from the 40s and 50s with polyethylene catheters and material science-based technology, and that the various shapes of catheters have been devised by by companies, and giving wide advances in the diagnosing and treatment of the heart disease, as we'll talk about. And unfortunately, there's a personal story that he was a member of the Nazi Party, and when he won the Nobel Prize, he was in the POW camp in London. Now again, how science can be interpolated. That the penicillin fungus that was accidentally discovered by Fleming in 1930s and was scaled up for production during the war for treatment of not just strep infection, but also for venereal disease, syphilis, and that has reduced the heart disease. And the syphilis, by the way, can cause aneurysm of the aorta, and that can rupture and cause sudden death. And at the same time, the beta hemolytic streptococci can cause scar tissue of the heart valves, and cause a disease called rheumatic fever, and that cause valvular abnormalities, and that can be treated. So by reducing the number of infections, uh, heart disease can incidence. Now, the other common abnormalities is called common cause of blue baby. Blue baby occurs due to mixing of the uh, uh, impure and pure blood, deoxygenated and oxygenated blood. Now, when you were connected before birth, you were connected to your mother through umbilical cord, and there was a hole inside the heart, which was called foramen, which connected the left side and the right side of the heart, and provided oxygen. You're, a parasite literally to your mom. Okay, and with the exposure of oxygen, the sensitivity changes, and this flap inside the top chambers closes. And now sometimes nature goes, and if it doesn't close, and at the same time, if there are other genetic abnormalities, including the narrowing of the valve, then the pressure gradient reverses between the low pressure right-sided chamber and the high-sided left-sided chambers. And when the two blood flows start mixing, then the lack of oxygen causes cyanosis, or bluing of the fingers and toes and lips. It's called blue baby. And this is tetralogy, this abnormality occurs in 1 out of 2,000 cases. But when you talk about millions of people, that's rather, can be a cause of sudden death. And so this was, and now this is all due to shunting and mechanical thing. And a pediatric cardiologist named Helen Taussig, took this up as a challenge. And in order to avoid this mixture of the heart, which was occurring due to higher pressure on one side, she decided to create a channel from the high pressure to the low pressure side, with creating a shunt. And the surgeons were reluctant to undertake that, but after some cajoling and persuasion, she was able to convince a surgeon named Dr. Blaylock to work on this at Johns Hopkins Hospital. And you can see that in this little diagram, they were able to create a shunt, which from the high pressure chamber to the low pressure chamber, again, improving the blood flow, okay, to the lungs. Okay, so this got to be named as Blaylock Taussig shunt. And luckily, the material that they were to use was the Dacron and polyethylene fibers that were created by the DuPont company, and simultaneously discovered in Britain as well. And this was used as a graft. And this later on was widely used to collect the abnormalities of this tube called aorta as well. So the Dacron grafting and the material science has played a huge role in treatment of heart disease and saving blue babies. Okay. And again, I mentioned earlier that COVID cardioplegia is important, and during the early days of heart surgery, if the normal temperature fluids were used, the heart did not tolerate that well. And varieties of scientists, and anesthesiologists who trained along with Dr. Blaylock pioneered the use of cooling the blood and using blood as a cardioplegic solution with various anesthetic agent was used, and that improved the survival rates, during heart surgery. Okay, so I think we've talked enough for this time, and this is where we'll stop at this stage and continue the various advances that took place as time goes along, and including ultrasound and other technologies that are used for diagnostic and therapeutic purposes. Okay, I'll stop right here. Stop the